physicists, welcome to Standard 6.2. We're going to start this standard off by taking a look at a very specific kind of mechanical wave. So in 6.1, we defined longitudinal waves and we defined transverse waves and all of their details, but we didn't really get into any of the specific waves. So today we're going to focus on one of the most ubiquitous waves around us that we use to communicate all the time, and that is sound waves. So just a few things in this video to give you some details about sound waves themselves. The first one is that all sound waves are longitudinal waves, and that's something that's kind of unique to sound waves in and of themselves. So all sound waves are longitudinal. The easiest way to kind of imagine this is to look at this thing called a tuning fork. And if you've done music before, you may have encountered a tuning fork, but basically it's just a piece of metal that's manufactured with two tines. So it's kind of like a fork you eat with, except only two, and they are large and thicker. And when you strike it on something, they vibrate at a very specific frequency. We've talked about frequency before, right? So when those tines are struck, then they move the air around in a pattern that makes a longitudinal wave. I've got a really quick video here for you to see what this looks like. So let me show you this real quick. So this string is acting kind of like one of the tines of the fork. And you can see these kind of white dots that represent some of those air molecules. And you see how those air molecules are moving back and forth. They are moving in the same direction as the wave itself is moving. That is what we're taking a look at. So that is an example of a sound wave. So when a sound wave propagates out from a tuning fork, it starts with this little compression right here. And then that compression propagates outward, sending that information out into the medium. That's an important piece of information, the next thing to say about sound waves. And that is that sound waves must have a medium through which to travel. So if you like to watch sci-fi movies or any of those kind of fantasy type things, and you imagine an explosion, kind of like the one I have here of this TIE fighter being blown up by the Millennium Falcon, in the movies, they have this big that happens, right? But the thing to know is that in space, there is no air, there is no medium through which that sound wave will travel. So there will be some motion of gases moving this way, but those gases aren't going to propagate a sound wave out in the same way that we would imagine in a movie, okay? So it's another big important thing to know about sound waves is that they must have a medium through which to travel. No medium, no sound. We can figure out how fast a sound wave moves if we know the type of medium through which it's traveling. So sound waves can travel through solids, liquids, and gases. The speed of the wave depends only on the medium's density. You know from chemistry or from other science classes that the density of a material is basically how tightly packed the molecules are within that material. We know that solids have a higher density generally than liquids, and those are higher than the density in gases. So if you think about that video that we watched with the propagation of those waves outward, if we imagine how fast those molecules would move, it's going to take longer for that wave to travel through from one molecule to another in a gas than it would in a solid where they go bonk, 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 bonk really fast, okay? So it's going to, the sound wave moves faster for a medium with a higher density. And you can see that in these tables that I have here. I've got looks like 5 different media here, from air to water all the way through to aluminum, and the speed of sound of a sound wave in that medium. So in dry air, sound moves at about 343 meters per second. Now, if you need a kind of a rough estimate of what that is in terms of how fast that is in miles per hour, that's approximately like 750 miles per hour. That's pretty darn fast. But as we move up in terms of the density, like for water, the sound wave is going to move at something on the order of like 3,000 miles per hour. And when we move even to a more dense medium like aluminum or steel, those more dense metals, it can move up to 10,000 miles per hour in those media. Okay, so the density of the material based on where the molecular structure matters. Also, the temperature matters, and you can see that in this second chart here. The higher the temperature, the more dense that material is, and therefore the faster the sound wave travels as well. All right, so even though the density of the material matters, and that alters the speed, one thing that doesn't alter the speed of a sound wave is its frequency. So one thing that I want to point out here first is if you are a musician, you've probably heard the term pitch before. Maybe even if you're not a musician, you've heard that term. Frequency and pitch are very closely related. The higher the frequency, the higher the pitch. Okay, pitch is something that is perceived by the human ear, whereas frequency is that very specific number of cycles per second. So as a physicist, when we talk about those sound waves, we talk about them in terms of their frequencies. An audible frequency, what we can hear, is somewhere between 20 and 20,000 hertz. Okay, so 20 hertz would be 20 cycles per second. 20,000 hertz would then, be 20,000 cycles per second. That is kind of the average range for human hearing. Now, that is altered by a lot of things. Everybody has different ranges, just kind of by nature. But also, when you listen to really, really loud music, like if you put your earbuds in and then you listen to really, really loud music, that can affect your hearing range. And then also, just by virtue of aging, your hearing range diminishes. But this average, this 20 to 20,000, is kind of on average what a human can hear. Any pitches below 20 hertz are called infrasonic. Okay, and an example of an infrasonic sound wave would be the wave that is generated from an earthquake. It can also be a wave that's generated by like large trucks that are driving on a highway. Just that kind of rumble that happens. If it's low enough, it can be an infrasonic sound. Above the audible range, we have ultrasonic. Okay, and again, that audible range is that average for the human, but different animals have different ranges of hearing. You may have heard that dogs have a higher, or their range of hearing goes to a higher frequency. Dogs can hear up to about 40,000 hertz. So you may have heard like a whistle that's used to train a dog, and those are really, really, really high pitched, so much so that usually we can't hear them, but a dog can hear it, right? And bats use their ultrasonic sound waves to hunt. You may have heard that as well. Bats can actually hear up to 100,000 hertz. Okay, so that's kind of cool as well. One other note about ultrasonic, you may have heard of an ultrasound, right? When somebody is when there's like a medical investigation that needs to happen, sometimes they use ultrasounds. They also use this often for pregnant women when they're trying to look at the fetus. They'll use ultrasound technology, and all they're doing is sending very, very high frequency sound waves into the tissue, and those reflect off of different things within the body. So like I said, that sometimes can be for a woman who's pregnant, but it can also be for lots of different tissue related medical procedures. So ultrasound is also a good medical description of using those high frequency pitches. The last little piece that I wanted to share with you, because I think that this is really important, is that different frequencies all travel at the same speed through the same medium. I'm going to say that again. All frequencies travel at the same speed through the same medium. So it doesn't matter if it's a really, really high pitch or a really, really low pitch. They all travel at the same speed. And the evidence for this, the thing that you can think about if you're trying to convince yourself of that, is that when you listen to an orchestra or a band or any sort of musical performance, the sound that you hear from the flutes or from the violins, from those high-pitched instruments, will travel at the same speed as the sound that comes from the tubas or the basses or whatever, those low instruments, because they all travel at the same speed. We'll come back to that a number of times during the standard, so I just want to make sure that you caught that. Hope that this was helpful and have a great day.